So today I'm going to be talking about how children discover mathematical structure through relational mapping. And I'm going to be focusing on a program of research that I carried out mostly with Linda Smith, but actually Dedri was a consultant on this project. So it'll be fun to see her reaction to all of our findings too. I also worked with two wonderful postdocs, Corey Bauer and Lei Yuan, who are both in faculty positions now. This isn't a direct, the studies aren't a direct test of analogical reasoning. They are investigations into how children make sense of mathematical symbols. And I think there's at least indirect evidence that relational mapping is underlying a lot of that growth. So how do I advance my screen? Okay, now I can't see any of you. So
you can't see your screen either, actually. Have you started?
Oh, really? Oh, I haven't started sharing. That's why. Okay, let me back out. And then I need to do this and this. There we go. Now, can you see it?
Yes.
Okay, back on track. All right, so when we think about mathematical symbols, it may be easier to start with something simple like how children understand the earliest count words, the smaller numbers. But even in these, small numbers, you can see that to understand what numbers are and what the symbols mean, you have to do a lot of mappings. You have to recognize the numerals. You have to see that the numeral 1 goes with the word 1, that it stands for one thing in the world, and that you can represent that with more abstract things like dots. And so I've long been interested in how children work out these mappings, and I did a lot of work on small number mappings earlier in my career. But what I wanted to talk about today are more complicated mappings that have to happen for multi-digit numbers like this. So you're all well-educated adults, you can read this number and immediately know what it means. But if you really stop and think about it, it has a lot of information packed into it. We can expand this number into its actual meaning by using an equation like this. And what you can see is that multi-digit numbers are using the spatial position of the digits to tell us what unit is being counted, essentially. So the digit on the far right is counting ones. How many ones do we have? 2. The digit to the left of that is counting tens. How many tens do we have? We have 3. And that's how you get 532 or any number going up as high as you want to go and actually going down into decimals as well. So I've started to call this count unit syntax instead of place value, even though place value is, essentially pointing to the same thing, because I think it's important to realize that when children are unpacking the meanings of multi-digit numbers, they're actually learning this, what you could call a syntax, because it has elements that you can combine in different ways to yield different quantities. And there are rules that govern how you put them together. And so I liken it to learning a syntax in English, or in any language, although I recognize there are important differences too. So when we look at the research on how kids do when they're learning place value, it's pretty consistent that it's extremely difficult for many children. It takes a long time. Some children struggle with place value tasks well into the upper grades at age 9, 10, or 11, which is years after they've been introduced to these concepts in school. When children don't master place value, they have a lot of problem with advanced arithmetic, like these problems. And you might be able to, understand why, because how are you going to subtract 19 from 70 if you don't understand that you're dealing with 7 tens and 0 ones? If you use the operation where you borrow a 10 from the tens column and you move it over to the ones column, that doesn't make a lot of sense if you don't understand that it's 7 tens plus 0 ones minus 1 10 plus 9 ones. That makes sense. So difficulty with this kind of blows up later in childhood. So you might be kind of surprised to hear about the first set of studies I want to tell you about, where we probed very young children's understanding of multi-digit numbers. We started off, this was a separate project that we did about 10 years ago, and part of the project was aimed at trying to understand how to help children in, the early elementary grades do better with place value. But we also probed what kids know before they get to school. And we used very simplified tasks like this, where children were shown 2 cards with numbers written on them. And then they were simply asked, which of these numbers is 429? Now, if you know what count unit syntax is all about, you won't have any trouble with that. But what if you didn't know all there was to know about count unit syntax? Is there a way that you could make a good guess here? Any thoughts on that?
I would be looking for a 9.
Yeah, a really easy thing to do here would just be where's a number with 9 in it, because only one of them has 9. Any other tricks or heuristics you can imagine kids doing there?
You give 3 numbers, so the one that looks like 3 numbers, 4, 29.
Yeah, good. So you're getting some kind of rough mapping maybe between the number names and the number of digits. You could say maybe they're learning that we read left to right in English. So if I hear the numbers in that order, I should see them in the left to right order. So these tasks weren't meant to, probe sophisticated understanding of place value necessarily, but just sort of what kind of emergent understandings. Same thing here. We had another version where we showed them numbers on cards and then we asked them which number is more. And here again, if you know the syntax of place value, you're going to quickly know that it's 429. But what if you didn't? Is there any way you could figure it out?
Maybe you look for which has got more numbers.
Yeah, you don't even need to know like specifically, just longer numbers mean more. So I'm always going to go with a longer number. Yeah, good. So so these tasks permitted that kind of reasoning, but I think that they're still interesting because they show us when children are beginning to pick up on these patterns. And when we gave those to children in kindergarten, 1st and 2nd grade, which correspond to roughly 6 years old, 7 years old, and 8 years old, we found that the older children were pretty close to ceiling on those tasks. Now, in the United States, we don't normally introduce place value instruction until 1st grade. So I'm thinking that these kids might have been in spring, so maybe they were responding to the instruction that they were getting. But kindergarten children don't normally have exposure to place value instruction in school. And so that was kind of an interesting finding that even they were getting 70% of the items correct, which is well above chance. So we pushed it down to younger kids, and we found that even they have a glimmer of some understanding. Even if you push it down to 3 years old, they're starting to pick up on some of those structural elements and they're guessing better than chance. Most of the time they're wrong, but not all of the time. And that's amazing that at that age, they're able to do so well. So we already talked about making good guesses, so I'll skip over that. So you may be thinking, like I started to think, that this is maybe a case of structure mapping. And, Dedry Gentner has done a lot of brilliant work on explaining the processes of comparisons and how people gain information from making comparisons. And that's what grabbed my attention, because it seemed like this might be a case where kids were actually extracting this information about place value from trying to make the mappings. So as she showed in examples like the science example, there are many ways that you can align different concepts or all kinds of structures. And they have lots of different components to them. And what she has demonstrated in her research is that, if people can just get a foothold by recognizing one of those that engages this process, that through comparison reveals additional points of alignment. And I started to wonder if that wasn't what was happening for kids with place value, because in those preschool studies, they weren't getting all of it, but they were getting some of it. And it seemed like that might be the foothold they needed to make further progress. So building on that idea, let's look again at the place value system. So what are the mappings like here? Well, they've got written numerals, which are, we listed a couple examples on the left here. You've got the number names, and you've got physical quantities in the world that you need to map those to. In the tasks that I just described, mostly what the kids were doing, we were asking them to map between the written numbers and the number names. But there was some with the which is more, there might have been some understanding of the referent quantities there. So this is a pretty complicated mapping system. This is just a small piece of it. And, kids are getting, little bits of information. So I'm going to say a little bit more about that in a second, but let me tell you about another finding that really, I think, provides strong evidence that kids are picking up on the structure here and trying to figure out the regularities. So Lisa Burge, who was a student at Indiana University, did this great study, excuse me, asking preschoolers to write 3-digit numbers. Now, if I asked you to write a number like 642, you would write like this. That's the conventional notation. But what Lisa observed is that kids made a lot of different errors. The errors on the bottom here are kind of random. They either wrote some symbols that might have been letters or who knows what. They might have written random digit strings. But the error that really grabbed our attention was this error, which she called the expanded error. And in this case, the kids were adding zeros in. And it seems like they're trying to make the place value system more transparent and regular than it is. It reminded us a lot of the errors that kids make when they're learning grammar, like over-regularizing verbs. So you might be aware of this in developmental psychology that, children often start off when they're learning verbs that have irregular forms, and they want to make them regular, like the regular forms. So in the past tense in English, we would say, I jumped with an ed on the end. But there are a lot of verbs in English, like I ran, you don't say I runned. But kids go through this period sometimes where they say I runned because they're trying to make it more regular than it is. And this seemed like a case of that, where they were making the number system map onto what they were hearing in more perfect alignment than what was actually available in the conventional written symbols. So here's the distribution of those error types by age group. This was a cross-sectional study. And what we see here is that at 4 years of age, kids are mostly doing the other. Those are those sort of random errors. And starting at 5 years of age, the expanded error becomes the most frequent, and that's a significant change. At 6 years of age, it's still mostly the expanded error, but you can see here that the conventional responses are increasing. And this is about the age when kids start to get instruction in school. So all of this is happening before they've really been taught anything formally. Okay, so here again, I feel like, this may be further evidence, indirect, albeit, that kids are trying to make mappings between the elements in the symbol system for place value, and they're trying to find the regularities using probably some kind of a comparison or structure mapping process. So what do we know about structure mapping and how people learn from, comparisons and finding patterns more generally? Well, we know that when things have a lot of similarity, that supports comparisons. High similarity matches are easier to make. When learners are making high similarity comparisons, they can often go from the high similarity to the lower similarity. And that low similarity comparisons are harder to recognize without some kind of cueing. So in general, it helps to have some surface similarity, maybe where, you know, you at least get started in the process. Well, when we look at place value, what do you guys think? Do you see a lot of surface similarity there across the elements that would help children? Yeah. Okay, so these numbers are, they're, you know, pretty arbitrary. You know, we just have to learn them. There's something about the structure of them, the zeros in there, that has a structure that's not arbitrary, but the other parts of it are. The words in English are hopeless for 2 digits. So the teens, for example, in English, we say 13, 14, 15. That sort of seems like it has a 10 there, maybe, if I, you know. Compare that to how they name numbers in Asian languages like Chinese. So in Chinese, they would say 10-1, 10-2, 10-3. And there you have a much more transparent alignment between the word and the symbol. Here, I would argue that it's practically non-existent. I mean, the kids may be able to figure out that TY means 10, but it's not going to be, it's not given to them. Whereas for the hundreds, now maybe we're able to see some structure. So 300, 400, 500, the number names in English at least map on nicely to those written digits. So that's a barrier, is my main point. And I guess I would say I find it doubly now astounding that very young children are starting to pick up on the structure when they haven't got a lot of similarity that's helping them. Similarly, we know from more general research that it helps people extract patterns when they're predictable. And we've seen this demonstrated over and over again. When there are statistical regularities, human beings are good at picking up on those. And when there aren't a lot of regularities, it's confusing and it's a lot harder. Now, if we look at, for example, how Montessori taught place value, she did a great job, I think, of highlighting the structure, pulling it apart in a very, representationally consistent way, using spatial alignment, creating materials that really help to illustrate the difference in magnitude from tens to hundreds to thousands and a lot of other parts. But that's not how these preschool kids are experiencing place value for the most part. For the most part, they're picking it up on packages, phones, they're seeing numbers on, boxes, speed limits, addresses. Do these seem like predictable patterns to you? So, I think there's probably comparison happening and, analogical mapping happening, and it's happening with just shreds of evidence. Okay, so what I've shown you so far is that children begin to interpret place value long before they're taught in school, and with some success. And that this ability improves from 3 to 7 years, where it reaches ceiling on very simplified tasks. They seem to be doing this despite sparse data, irregular patterns, and opaque elements. But we also know, and don't forget, that this is a very difficult thing for most children to learn, and that some of them, have trouble with it well into middle school and don't do so well on other tasks, right? So that raised the question, why? And that's what I'm going to focus on the rest of this talk. But I can pause here for questions if people have any on the first part.
We've just had a question come into the chat. Apologies if I pronounce your name incorrectly, Simj. Does it create any problem for kids that Americans that usually do not read out numbers like 429 or 429 as 4 Simji, sorry. Does it create any problems for kids that Americans usually do not read out numbers like 429 as 429, but shortly say 429 instead, especially for things like door numbers?
I think that's a good
Different
hypothesis.
pronunciation.
Yeah, I don't know. I don't have direct evidence, but that would definitely be in alignment with what I'm thinking. It makes sense that it would be difficult. I mean, on the one hand, you could say, if you've been hearing 429, and then you have to map that to the written number, that's less difficult because you don't have all those unit words in there. But ultimately, you're not going to understand what it means. Like, you might be able to do that one task on a very surfacey level, but you're not going to understand the underlying syntax until you get the unit names. Great question. Okay, so I was kind of worried about how we could have these preschool children who start off with so much understanding and they're really working hard at it. They're clearly engaged and they're doing whatever they can with whatever information they've got. But on the other hand, all this mountain of evidence showing that older kids are having trouble. Where's the disconnect coming from? And at about the same time, I was doing field work in a school district that I'm, I have a relationship with, and they're serving a low income population with a lot of kids who are struggling. And I started to volunteer there, and they put me to work doing a bunch of different things. But one of the things they asked me to do was meet with some of their lower performing kids and just try to tutor them and figure out what was happening. And so while I was doing that, I made up this game with them. At first I thought, well, they just need to understand that a 10 is a thing you can count, just like I can count my fingers, or I can count these blocks, I can count tens, I can count hundreds, that basic understanding might be important. And so I had them construct tens using these dried beans and little condiment cups. And we would count 10 into a cup and put the lid on and put it over here, and then count 10 more into another cup. And we'd say, there's 10, there's 10, there's 10, and talked about that quite a bit. But I wasn't sure they were getting it. So I set up scenarios like this where they had the condiment cups and some loose beans, and I'd ask them to count them. Now, people who are aware of base 10 units would probably count this either 10, 20, 30, 31, 32, 33, 34, 35, 36, or they might go 1, 2, 3, 4, 5, 6, 16 if they're really like a challenge, 16, 26, 36. But these kids, though, these were in first and second grade, these children. What they often did is they would say, oh, 1, 2, 3, 4, 5, 6, 7, 8, 9. So with no recognition that they were crossing a boundary, that they were no longer counting the same thing when they went from tens to ones. And because we had worked so long making the tens, I would stop and remind them, well, wait a minute, remember this has 10 beans in there. That's not one bean, saying the unit, that's 10 beans. So we can count that 10, 20, as we had done many times before. But sometimes the kids would say, oh, right, 10, 20, 30, where's my pointer? 40, 50, 60, 70, 80, 90. So making the same error in the other direction. And I began to think that that might be where a lot of the action is, that it's really, you can get bits and pieces of the system informally, but it's understanding the syntax that is going to really trip you up in the long run. If you can't understand that these are units being counted and the units shift as you go from one place to the other, you're going to have a hard time doing anything else. And I wanted to find out more about why, if that was what was really tripping them up, and what was happening there. So, so the hypothesis is based on the observation that these early mappings that kids are trying to do informally are yielding partial information, but it's not enough for them to fully comprehend the structure. And that weak syntactic understanding of counts and units could actually fly under the radar in the lower grades, because depending on how you measure what kids know about place value, if you use a task that allows you to do some of the tricks we talked about earlier, it might look like they understand a lot, but it's still going to blow up later on when they have to do carrying and borrowing and other operations that rely on place value. So I guess the first question to ask there would be, are these really different understandings, or is this just, are all measures of place value tapping the same thing, or are they tapping different understandings? And if they are different, is this early understanding that's partial and kind of not quite right, is it harmful? Like, does it keep kids stuck, or is it helpful? And so the next project I want to talk about is one that I just finished with Linda, and all the papers I'm presenting now are either new this year or in press. So we did a longitudinal study of children starting in kindergarten and tracked them to 2nd grade. And in this first paper, what we did is look at the transition from kindergarten to, or I should say, we tracked them until 2nd grade. And in this paper, we're tracking just from kindergarten to 1st grade, the changes in place value understanding. And based on the hypothesis I just described, we gave the kids 6 tasks, 3 place value tasks that we thought would permit some kind of partial understanding. So magnitude comparison is just saying which number is larger, like the which is more task I talked about earlier. Transcoding is Lisa Burge's task, where she had them write multi-digit numbers. And we threw in number line estimation there too, because it seemed like you could place a number in the correct place on a number line without decomposing it into its counts and units. You could kind of roughly know 55 is somewhere in the middle there on a 0 to 100 number line. And then we chose 3 other tasks that seemed to pin kids down more on the syntax. Maybe not 100% perfect. There might be some heuristics kids could use there, but it just made it harder. Oh, here I've got pictures of these tasks. So there are the 3 approximate tasks. And then here are the 3 syntactic tasks. So we used a task that actually Chan developed in 2014, and it's a lot like the one that I did when I was out doing my field work with the beans and cups, where you have the kids count across base 10 units. But what they did is use line drawings of base 10 blocks that kids, may be familiar with in school. But it's the same thing. So this you would ask and see if they can count 100, 110, 120, 121, 122, 123, 124. And they had done some really nice research showing that performance on this task in 1st grade was highly predictive of later math achievement. But they hadn't necessarily compared it to all the other place value tasks that are out there. So that was one. We also used expanded notation, which is commonly used on standardized tests where kids have to match the equation to the multi-digit number. And then we made up a task called which n has, it was inspired by Camille's digit correspondence task, where she'd show them a written digit and say, what does the 6 mean? What does this 1 mean? And we wanted to make it a multiple choice version. So we said, which number has 3 10s, which number has 6 1s, and had them point to the number that matched. Okay, so the first question is, did performance differ on these 2 kinds of tasks? Or is this distinction only in my mind? And this is a kind of complicated graph, but I wanted to share these violin plots because I think they're so great. What it's showing you here is, I'm just going to talk about this one to orient you. So this is the base 10 counting task. This is how kids performed in kindergarten and 1st grade. And this was the low scores and these were the high scores. These are the same kids. So here they were in kindergarten and here they were in 1st grade. And this is the same graph for transcoding. So how did they do? I keep losing my pointer. How'd they do in kindergarten and how'd they do in 1st grade? And here you can see they're approaching ceiling by 1st grade, but they started off kind of middling. Here they started off kind of low, but they got better, but they weren't anywhere near ceiling. So you can kind of quickly look at these plots and probably see that over here on the syntactic tasks, the performance wasn't as good. Like here, they're rapidly getting to ceiling on magnitude comparison and number line. So it seemed like approximate tasks were easier for kids, and we tested that statistically and it panned out. They were, so they definitely do better on approximate tasks. Does that mean that they're separate? Well, to find out, we did a confirmatory factor analysis at each grade level. And we tested a 1-factor model and a 2-factor model. And if they both had good fit, we compared them using a chi-square test to see which one was the better fit. And what we found in kindergarten was the 2-factor model was the better fit. And as we predicted, all 3 of the approximate tasks loaded significantly onto 1-factor, and all 3 of the syntactic tasks loaded onto the other factor. So that provided evidence that they were separable. Those factors were also highly correlated, so it's not like they're picking up on completely different things. They're covering the same territory, but there may be some difference in the latent construct that you're tapping with an approximate task. By first grade, however, a 1-factor model was the best fitting, and there was no benefit to the 2-factor model. So it's as if the 2 factors converge by the time kids are in first grade. So there's some kind of integration happening. Okay, so is this early understanding different? Yes, it is. Now we turn to the question, is it harmful? So it's possible that if you're really good at like approximate heuristics and little tricks and things like that, that it could keep you from learning place value for a while, because you can actually skate by. And it might take a lot of effort to actually unpack a multi-digit number into its units and counts, and kids might resist that. So it could actually backfire on kids. Alternatively, it's possible that having that partial understanding is really necessary, that you can't even get into this complicated symbol system unless you've got something, and having those bits and pieces is a necessary stepping stone. So to test those ideas, we did latent path analyses where we used the 2 factors in kindergarten to see whether they predicted the 1-factor in first grade. This is just looking at their place value understanding. And what we found is only approximate place value understanding was a significant predictor. Whatever early syntactic knowledge kids have in kindergarten actually didn't help them. Now that might be because there was very little syntactic knowledge in kindergarten. Maybe there wasn't a lot of variability there. That's one possibility. The other possibility is that maybe kids are getting those syntactic tasks right using some other, heuristics that I haven't figured out yet. But the really interesting piece to me is that there's definitely a boost for having strong approximate knowledge. As I said at the beginning, we also tracked these kids into second grade. We didn't measure place value understanding in second grade. We focused on calculation because I was, trying to understand what would cause kids to suddenly not understand calculation in the later grades, and what teachers might be able to do to predict and identify those kids in kindergarten. Also, the kids had reached ceiling on all of these tasks, so we didn't measure place value, but on the calculation test, we found the same pattern. So if we look at kindergarten, approximate knowledge and syntactic knowledge, only approximate knowledge predicted children's calculation skill in second grade. Okay, so in answer to the second questions, early approximate knowledge predicts later syntactic knowledge and later calculation skill. It is definitely helpful. Any questions on that before I move on?
Yeah, there's a couple of questions from Akshita. I don't know if you want to ask them yourself, Akshita, or I can read them out. But I'll start.
So I guess a little more context for the first question would help. So I was referring to the task with the beans. So do you think that one source of difficulty with that task is because children have difficulty switching flexibly between a representation of a single 10 as 110 versus a thing that also contains 10 units and 10 ones. So that was the first question.
Absolutely. Yes, absolutely. It does kind of remind me of like some of the things that Piaget talked about, where it's difficult to coordinate two different ideas at the same time. And so you have to understand what a 10 is, you have to hold the idea of 10 ones separate from the idea of the unit itself, or somehow coordinate that understanding. And I think that's a good insight.
Mm-hmm. And the second question was about the slide that just came before this. So in first grade, when you say place value tasks, are they the same tasks as the kindergartner syntactic tasks? The previous?
Yes, they were the same.
Okay, great. Thank you so much.
Here, yep, you bet. Okie doke. So what's happening here then? We've established that kids start off with this early partial, maybe inexact understanding of place value that ends up being pretty important developmentally. And we also know that kids have a lot of trouble later on. It seems like they're having trouble with the syntactic piece. How do they get from one level of understanding to the other? What is actually happening here mechanistically? Well, one pattern that comes to mind is what has been shown in other research areas with children learning complicated concepts like this is what I would call a general to specific attunement. So, for example, Kathy Sandhofer showed that when kids are learning color words, at first when you ask them what color is it, they give you a color word, but it might be a wrong color word. What they don't say is it's bouncy or it's plastic, or they don't just give you random words. So they get some awareness of the category of color, and then they gradually get more specific and exact. And it seems like that might be part of what's happening here, that kids start with an approximate awareness of place value and some partial knowledge of base 10 structure, and that they're kind of tuning into the specific mappings. So that's one idea. If we go back to, thinking about this in terms of structure mapping, it's consistent with the idea that you're discovering the new structures by making comparisons. That the process itself has to start with some kind of mapping, and then once you engage in that mapping process, it's going to start to reveal all the other parts of the system. So to get a better sense of how the system is organizing itself, let's look at this terribly complicated visual, because I want to back out of the whole idea of approximate and syntactic for this next part, and just think about what are these individual tasks measuring. And if we think about this system in terms of what are the mappings, this is where I would put the different tasks relative to this figure. So here we've got base 10 counting, and that's a mapping between the number names and some kind of physical quantity. Transcoding, where we ask them to write the numbers, is a mapping between I hear the number and I write it. So it's between the two symbols. I would say expanded notation, in which has 3 10s, are just queries about the written symbols themselves. So there may not be a lot of mapping happening there. There's a little bit of verbal maybe in the which n has. And then we've got number line, in which are probably mappings between the written numerals and some sense of the physical quantity. You don't actually have a physical quantity in front of you like up here, but there may be a sense of like numerical order mapping onto magnitudes. So when we look at these tasks in terms of, as individuals, how can we get a sense of their relationships, their interrelationships, and how those change over time? Well, one of the papers that we published just this year that was led by Corey Bauer used a network model. And these are often used in, like organizational to model things that are happening in an organization or in social networks, trying to map out relationships between people or between entities. And the way they work is that they simultaneously calculate the pairwise relations between all the elements in a system. So it's sort of calculating how related they are like you would in a regression, but it's at the same time weighting that against all the other relations. And these models yield really wonderful visualizations that show you, what are the central parts of the system, how closely related are those to each other. And these models can end up being all different kinds of shapes and organizations. It just depends on the data you've got. And I loved the idea of doing this as a bottom up. So everything I've talked about so far has been sort of taking our hypothesis and imposing that on the data. But in this model, we were really allowing the data to tell us what was happening. So we put the 6 tasks that I've already talked about into this network model, and it yielded these representations. What you're seeing up here is the knowledge network in kindergarten. And I hope you can see the little labels, but we've color coded it too so that it's, maybe a little more helpful. What you're seeing here is that, first of all, these tasks, the number line, magnitude comparison, and reading and writing numbers, which is transcoding, clustered together. And they did that without, this wasn't a confirmatory analysis. They just were significantly clustered. And the same thing was true for the syntactic tasks, base 10 counting, expanded notation, and which number has. If you look between the 2 grades, so here it is in kindergarten and here it is in 1st grade, the basic network structure wasn't different. So there are tests that you can use to compare the network structure, and we didn't find a significant difference between kindergarten and 1st grade in just the shape of the network, if that makes sense. But the strength definitely increased. And you can see that represented here by heavier lines. That's showing a stronger relation. And also the distance between the lines. The other interesting feature of these networks is that they're organized around these 2 tasks, base 10 counting and transcoding. So they're at the center of the network, and everything else is connected to each other more or less through these central nodes, and that just becomes, more the case in 1st grade. Now let's look at transcoding. That's that task where the kids write the numbers and they make that really interesting expanded error. And it was an approximate task in our factor analysis. Well, here it is, reading, writing. In kindergarten, it clusters with the other approximate tasks, but in 1st grade, it jumps ship and it becomes clustered with the syntactic tasks. And probably for a lot of kids, this is when they go from being partial and guessing, I got some good tricks here and I'm right some of the time, to, oh, okay, now I get it. Because that's where we saw the big shift too. By the time kids were in 1st grade answering those simple questions, they were at ceiling, remember? So we think that transcoding probably plays a very important role developmentally, because it has that property of allowing kids to make mappings that aren't quite right and take guesses that are, they're good guesses, but they're not based on full understanding, and use those to bootstrap themselves into figuring out the actual structure. And by the way, because transcoding was one of the approximate tasks, probably that explains why the approximate factor was so predictive. It might not have been as much the contribution of the other 2 tasks. And we see that also in this path analysis where this is sort of like a multiple regression, but using a latent approach and latent variable approach. And here we just looked at which tasks as individuals were significant predictors of the 2nd grade calculation. And transcoding was highly predictive, base 10 counting was highly predictive, and those were those 2 central nodes. Which number has also was. And this is kind of interesting because the syntactic factor on its own wasn't predictive. So we're still trying to sort that out. But I think the really interesting part is that even though these 2 tasks were part of the approximate factor, they didn't really show a strong predictive relationship on their own. It was really transcoding carrying the weight. So my answer to the question of how they figure it out, I think there's more to study here, but we can at least say that kids start off with a strong foundation of approximate symbolic number, meaning it's based on informal learning. This approximate foundation is highly predictive of syntactic place value and multi-digit calculation, but early syntactic skills are not, at least as a group, maybe base 10 counting and which and has are as individuals. Their knowledge structures for place value are built around the two precise mappings, the word to numeral mapping of transcoding and the word to referent mapping of base 10 counting. And that transcoding in particular has this interesting pivot going from approximate to syntactic, and it allows children to build their ideas from build and test not quite right ideas. And so here's just a reminder that, you know, if you have in the transcoding task, you have the opportunity to experiment with a lot of different solutions and then, you know, see if your answer is right and get that feedback. That probably is a really important building block for kids learning place value early on. And actually, I've spent a lot of time in schools and I don't see teachers doing this very much. So it could have a lot of educational value. And on that topic, I'm going to end with this last study where we actually tried a training that was based on some of the ideas we had going into this project. We didn't have the benefit of knowing the results of everything when we designed this study. So this is based on, you know, some of the other ideas I talked about, like, you know, helping children understand that base 10 units are a thing that you can count. So our lessons were about that and counting units. So creating tens and counting them over and over again to reinforce that idea. We also provided a lot of support for structure mapping because we hypothesized that that's probably the engine behind a lot of this learning that we're picking up with our other measures. And so if we made it really easy for kids to see the structure by, you know, aligning all the elements spatially so that they can see how they map onto each other, including the numerals. Here again, what I see teachers doing a lot is using materials like this, but they might use base 10 blocks on one day and do a worksheet on the next day. And there's not a lot of opportunity for kids to see the whole system laid out like this. Now, we'd started off with much simpler mappings. This is one of the later lessons, and we wouldn't jump in here. Especially because we targeted kindergarten children, and most of the time kindergarten kids aren't being taught place value in school. And they definitely weren't at the schools where we were working. So we started off with, you know, much simpler mappings like counting tens within this representation. And then next day we'd count tens within this representation and slowly built our way up to doing this big mapping. But you can see here how it would be easier for kids to pick out, you know, the ones here, and then this is what the number looks like, and this is where it's located. The other really important advance, I think, here is that we did what we call dense co-occurrences, which meant to us that you repeated over and over and over again what the mappings are. And I did this because, you know, when I was a teacher and what I saw other teachers doing is they might say, okay, see, let's make this number out of blocks. Can you show me 25? Okay, yeah, there's 25. Good. Let's do 37. Let's do, you know. And what we did instead is we slowed it way down. And we would say, okay, I made this. Where's my pointer? I made this representation with beans. I want you to make the same one with your blocks. Can you make you know, make your blocks look like this? And then they would create a representation. And without even having the numbers there, I'd say something like, okay, let's check and see, is it the same? Let's see, here's 10, there's 10, here's 10, here's 10. Yep, 2 10s here and 2 10s here. We call this 20. That's 2 10s. And we have 20 here as well, right? See, 10, 20, that's 2 10s, 20. And how many ones do we have here? It's 5. Did you get 5 ones in yours? Let's see, 1, 2, 3, 4, 5. That's right. 5 ones here, 5 ones here. So we've got 25, 25. And then we put the numbers down and go through the whole thing again. because thinking about these kids trying to pick up on regularities with not a lot of input, it seemed like it would help them to just lay it out and give them lots of reinforcement. So as they're thinking, oh, does this map to that? Does this, do these two correspond? If she said this is 2 10s, does that mean there's a 2 down here? These questions will be coming up in their mind, but instead of dropping it and going on to the next item, take the time to like say, yeah, this is 2 here because it's 2 10s and 2 10s, or it's 20. We call that 20 when this is, the 5 is gone, it's just 2 and 0, it's 20, right? Well, so unfortunately, this was an experiment that was a victim of COVID. We were supposed to do 2 cohorts and we got halfway through the second cohort when the schools shut down. But we analyzed the data on the first cohort, which is about half the sample we hope to get. Luckily, I work with a great statistician named Greg Hancock, and he had a lot of good ideas for maximizing our power. And what you're seeing here is the actual individual performance of each child that was in the study. And the kids in the control group are in red, and the kids in the experimental group are in blue. The control group did math problems, but they just did single digit addition and subtraction. And so when we measured their place value understanding after the training, we looked at both the syntactic tasks and the approximate tasks, and we found a significant increase in the slope for the experimental group on syntactic tasks. So there was an effect of the intervention, but it was limited to syntactic. It didn't help kids on the approximate tasks. And actually the control kids also improved on both. They just didn't improve as much on the syntactic tasks as the intervention kids. This was a long intervention. I forgot to mention, we did it, it was 20 lessons, so we did it over a period of about 3 or 4 months. So there was also stuff happening in the classroom that might have contributed. Based on our previous findings, we were also interested in whether this intervention worked better for kids who had the strong foundation of approximate or syntactic understanding. So remember, I'm trying to figure out how you get kids around that corner from the approximate to the syntactic. And I was thinking, well, maybe if you've got a strong foundation of approximate understanding, then this is the intervention that pushes you around to get that new understanding. But it wasn't true. What happened is the kids with the higher approximate test scores actually had more improvement in the control condition than they did in the intervention condition. So they were, in a way, maybe this is a little bit of evidence that it can get in the way because they were sticking to what they were doing and continuing to develop it. The higher syntactic pretest scores were associated with improvement in the intervention. So the ones who came in with better knowledge of syntax to begin with really shot up. So the intervention helped them a lot in the way I just described, I think, because they were figuring out the bits and pieces. And once we showed them the whole thing, they were like, yep, and they took off. So what I'm really interested in now is still, what do we do with the kids who don't come in with that, by luck or whatever is happening at home, come in with that stronger syntactic understanding? How can we help them make that big leap? That's a lot of words. I don't think we need to read through all of it. I think we've covered it. I just want to say thanks to all of you for being here today, and I want to thank all of my collaborators. I want to mention that intervention was designed with a lot of input from Dedri and Art Baruti, and I'm really especially grateful to them for that help.